Hi everyone, I'm Gabby, and today I'll be presenting my semester's work on the thermal design and analysis of the Polaris polar rover. So the motivation behind my project was that the polar rover would be subject to extreme temperature conditions on both the hot and the cold spectrum. And the initial design that the team had come up with would need to be analyzed and iterated so that it would neither overheat nor get too cold. So here is both the SolidWorks model and the artist's rendering of the polar rover. And here you can see the radiator is this white panel and the solar panels is this blue here. And this front here is also a solar panel. And here's the thermal desktop model of what I just showed you. So here, this silver box is the radiators I mentioned. You can see the side and the front solar panels. And this is similar to a finite element analysis software that you would use to calculate stress. In ANSYS, maybe some of you have used that. Only here, we're looking at temperature. And you can see all these nodes, these little bubbles on the model. And the temperature can be calculated at each of those points. And here you can assign the correct material properties so that the model will be accurate and the heat will be conducted and radiated properly. So in space, there's no air like we have on Earth. So convection, which is our most prominent form of cooling here on Earth, is no longer a usable form of cooling. So one thing that I did was I modeled all of our electronics directly onto the radiator. And this will enable the heat to conduct directly from the electronics onto the radiator, which will help dissipate the heat. And so our total heat is about 265 watts when everything is running. These heat boxes also enabled me to look at the individual temperatures of the electronic components at the end of each hot and cold case. Here's some of the component temperature ranges just to give you an idea of our ideal temperatures. The communications is what is our limiting component, and so you can see here everything needs to be between -10 and 50 degrees Celsius. Originally, there were some other components that the team had originally said maybe we'll use these, and these are the final components that I'm recommending for use based upon my hot and cold analysis. So here's my initial analysis, and this yielded a temperature range of the components between 19 and 91 degrees Celsius. So the hot side was becoming way too hot. And the cold side, it could be hotter or colder. The cold side was perfectly fine and in range. And so the problem I had was to come up with a way to iterate this design so that the heat would more easily flow from the hot side to the cold side. So to help demonstrate that, I've come up with a little cartoon. So this is how how Polaris was initially modeled. Things weren't connected very well. There wasn't any particular color assigned for paint for things. And so there's really not a lot of heat transfer. You can see the sunny side was just making the sun was making the sunny side hot, and that heat really wasn't traveling very well to the cold side. So here's another cartoon of the changes that I made. So I added a thermal bridge, which is what you can see right here. And that helps conduct the heat from the radiator on the hot side to the cold side. I also connected all of the radiators to the chassis better than they were originally connected. I also painted the inside of the radiators, the bottom of the chassis on the inside here, and the electronic components black, and that will help radiate the heat better within the rover. And so now we have both conduction and radiation, which are the two types of heat transfer that are possible in space. So here's a list of the changes I made. I altered some things about the solar panels. I connected things together, as I previously mentioned. I balanced all the heat loads. Previously, I had all of the hot things. I had a lot of really heavy energy things on one side, and so balancing the heat loads helped prevent that one side from overheating. And I painted the inside of the rover, and I put MLI on the radiators. So here was my new analysis of the hot case. You can see there's better temperature distribution throughout the chassis than there was before. And now our final hot case steady state temperatures are between 13 and 40 degrees Celsius, which is well within our operating temperatures of -10 to 50. So that was step one, was the hot case. And the next step was running the cold case. So the entire time that we're on the pole, we're not going to be sitting in the sun the whole time. For part of what they want to do with Resolve, it needs to venture out into the shade where there won't be any sun. So I conducted a cold transient analysis to see just how long could we venture out into the shade. And the Resolve people wanted about 2 to 3 hours, and I figure I can give them much better than that. So my cold transient, after 8 hours, yielded temperature ranges between about 8 and 20 degrees Celsius, so well within what they wanted, much more time than they originally wanted. So Resolve will be very happy to know this. And here's a graph of the temperatures versus time. So these ones up here are on the hot side, and these here are on the cold side. And I have a video for you to see of the heat flow. And this is again over an 8-hour period. So here are all my accomplishments for the semester. I modeled both the hot case for steady state and the transient cold case. I iterated this design several times until I came up with that final list of recommendations I showed earlier. I also made recommendations for the component selections. I wrote the thermal section for the ILDD. I made a blog with video. I also did some research earlier in the semester on variable emissivity coatings, and I determined that we don't really need them. Previously, we thought we would need them in case we were getting too hot or too cold, but it's pretty expensive, very hard to get a hold of, and black paint will do just fine, it turns out. And by Friday, I'll have my final paper. So I'd like to thank Heather and Steve for all of their help with Thermal Desktop, and John for all of his design iteration guidance, since I didn't have any previous intuition on how to iterate things for heat transfer in space without convection. Any questions?
The model is asymmetric from end to end because one end has a solar array. That doesn't seem to have very much effect on the longitudinal heat solution or variation, even though there are times when it shadows, and there are times we don't know what connection or model that you have end to end. You showed a cross section, you showed what you did there. So would you put up a distribution or two, and it can be anything from your initial to final, and just refresh us all on how much that end solar obstruction affects the heat distribution or the temperature distribution.
You mean, I don't think I understand.
Just put a picture up.
Okay. Of the model, this?
Yeah. If we look at the right image, the diagonal deck looks green, 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 and then you encounter the cold solar array. If we look at the left image, the cold solar array looks blue
I see.
on the end, and then the diagonal deck looks pretty uniform. And if we go to another distribution, it's, I'm not pinning you down to say this is the only one, because this really isn't your best illustration to show some variation. So there's actually one or two you have in here that show a little. And these don't show much because because the sun is coming in directly from one side
Yeah.
to another side, so it's not being shadowed.
So you're saying what happens when the sun, say, is shining on the front, or like maybe at a 45-degree angle?
I am.
I'm so glad you asked that question, because that brings me to my supplemental slides. So
There you go.
there you go. So I didn't want to put all of these because then it would be in too long. So looking at the front, you can see that it's getting really hot. In this case, I have it shining directly on this face, which is why this is warm. So the back side of this solar panel is actually not receiving any sunlight. And so the temperature ranges in here are about 5 to 17. And then for the 45-degree case, which you're curious about, it's actually a lot colder, and as you mentioned, that shadowing is a problem. However, the temperature ranges are between 25 and -4, so still well within our operating temperature range.
Did you analyze the 180-degree scenario where you're actually getting sun on the active side of the solar panel?
I did not know. Yeah, Heather.
So there is a difference between the hot case and the cold case. There's something going on with the radiator.
Oh yeah, so between the hot case and the cold case, there's going to be an MLI shield that will come out. So the MLI can't be on the hot case, which brings me to my other supplemental side. It's because it'll get too hot, because it will be too well insulated and the heat can't dissipate well enough. So there needs to be some sort of shield. If we don't have the shield for the cold case, it can only go out into the cold for about 3 hours and 20 minutes. That's all my supplemental slides. So.
What material did you use for the thermal bridge?
I think it was aluminum, about like a centimeter thick or something like that. Any other questions?
So none of this is for free, right? You
I worked
talked
for
about-
free, but
Oh, no, I mean, none of your results come for free, right? That you've, you said that you can extend the life of the rover for up to 8 hours.
Mhm.
But in the cold, what's the cost of that in terms of mass or in terms of complexity? Do you have a sense of, what you could do to extend that life even more, and what that would cost in terms of mass?
I'm not really that familiar with MLI, so I don't know how heavy it is. Maybe someone else in the class knows that more than I do. But I guess adding more of it would probably let you go for longer.
Is it more or less complex to have that MLI shield that it's deployed and retracted?
Thermally or mechanically? I don't understand how mechanically that will work, but
What can you speculate about, if you didn't have to do that, if the rover, as it was, no actuation, could just sit there and survive all of the thermal cases, versus if you have to put a shield over the radiator?
how much will that cost?
What's the difference in complexity?
It would be a lot harder to add the MLI shield.
And then, okay, so this is kind of out there, but if you wanted to go for like 24 hours, right, a really
Okay.
long time, what would you have to do?
Well, I was looking at this, the graph, and they actually seem to be reaching some sort of steady state value. I don't necessarily know how long that would take, but you can kind of see here, right, steady state thermally means that the slope and the temperature versus time plot kind of gets really small, right? And you can see here that this slope here is much smaller than the slope here, and this slope here is actually getting closer to 0. So I'm not quite sure how much long it would need to go for it.
The steady state for that is the temperature of the dark area, right? It's the
Well, so there's some amount of constant power.
Yeah, there's still
that-
power.
So you actually might not be able to get to 8 hours anyhow because your battery runs out.
Yeah.
I'm just curious.
Yeah.
Could-
What is there a point where what's the furthest that you could extend it without making the system
I see.
significantly more?
I see. Yeah, I would need to run a longer simulation. And they really only want to go into the shaded side, I understand, for about 2 to 3, maybe 4 tops hours. So 8 hours, I think, is ample time for whatever they want to get done. Any other questions? Okay.